So, this is a talk about megasas and VFIO. VFIO is basically the new generation on how to do device assignment on Qemu. There used to be, just a few seconds, this was the thing, right. Okay, so, PCI device assignment. Most of you will be, hopefully, are familiar with virtualization and so nifty things you can do with. Device assignment basically means that you route a PCI device directly to the guest without the host having to interfere. So not something like SEN where every I/O has to go via the host module thing, but rather that the guest can access the actual PCI device directly and work on it. So, main thing here is that obviously it's a virtual machine, so you need to access it somehow, where you have various choices like the normal classical emulated device, virtual devices. Then we have in Linux a concept called Vhost, which is basically accelerated Virtio, and obviously direct access to the hardware. So if you look at the stack, for emulated device, it becomes rather complex. You have tons and tons and tons of layers involved. You have the guest user and the guest. That talks to the kernel, to the block layer talks to the driver then talks to the driver emulation in the host, Qemu in this case. The driver emulation talks to the Qemu block layer, the Qemu block layer talks to the host block layer, and the host block layer talks to the host SCSI driver, and the SCSI driver finally actually accesses the hardware. So this is a bit of a tedious process and quite time consuming, which obviously means it's not really fast. I mean, it's totally emulated, so it's virtually indistinguishable. These both drivers are identical. So both think they're actually talking to real hardware. But still, quite a few layers. So to speed it up, there's something called Virtio, which basically means that the driver in the host has direct access to the structures of the driver in the guest. So it's a kind of back-to-back communication going on here. So the driver knows exactly where the queue is, the command queue is for the guest kernel, and just gets the commands, just access the commands directly. So you don't need to do any memory transfer, which is quite fast. But still, it still means you have to go from the host process into the host kernel and back down. So that's there's still quite some context which is involved. To make that, to streamline that even more, there's a concept called Vhost, which is, again, a back-to-back communication like Virtio, but this time it's a back-to-back communication between the guest kernel and the host kernel. So you're skipping the host userland, the host Qemu process altogether. So you're not going into the userland during I/O, but basically from one kernel context to another kernel context, which is quite fast, or one should say supposedly quite fast, because no one actually has measured this. And the Vhost driver then talks to the block layer, blah, blah, further on. And finally, we have device assignment, where we just skip that altogether and have this one talking directly to the hardware. As you can see, it's not actually directly to the hardware because it doesn't really quite work out as nicely. You do need to translate the addresses from the host kernel into the guest kernel, or vice versa rather. So if you do in DMA, the DMA addresses you get in the guest are obviously guest addresses. Whereas if you put the guest address directly on the host, on the DMA information for the real hardware, the hardware thinks it's talking into the guest in the host context. So it becomes rather confused where the data is. For this, you need an IOMMU to make that work, so that you can have that you offload the translation to the hardware. This one. So with PCI assignment, you can have a rather nifty access to the hardware, so you don't have any emulation involved. You can use unmodified drivers, and you actually have the real hardware talking to the guest. However, the PCI device is then visible in both the host and the guest context, if you're using KVM, or a Qemu, which means you have to prevent the access to assigned device from the host, for which there is a module called PCI stub, or if you're using VFIO, there's a PCI VFIO. So the PCI device assignment itself, problem here is that both have a different memory mapping. So you have the kernel mapping, which is basically a straight one-to-one mapping, and you have the guest context, which is somewhere skipped to a different, has some offset to into the host kernel. So the physical addresses, or that what the guest gets as physical addresses, are actually virtual addresses in the host, which, well, needs to be translated somehow. If you're running emulator, the emulation will do it for you. But if you're not running emulator, you have to have some other instance which does the translation. So, and as you're talking directly to the hardware, you can't really insert some magic bits in there to do the translation. So you actually need some hardware support for this, which leads us to the IOMMU. So you actually do need hardware support here, the IOMMU, which is present on most modern server hardware, one has to say. And, well, task is obvious to translate the memory addresses. Intel calls it VTD, and AMD calls it VI. But again, be aware, not every box which says it does VTD actually has an IOMMU and can do this trick. You need to look out for the DMA AR table if you have an Intel box. Only if you have this ACPI table, the machine can do DMA translation. If you don't have this table, forget it. It could say, yes, I do VTD, but in fact, you can't use it. The other thing is that the IOMMU is disabled per default because if you enable it, you have a performance loss, simply because the IOMMU needs to do translation for every I/O access, not just for the emulated device, but for every I/O access. And this means the IOMMU has to look up each and every address in its internal lookup table to figure out whether it is in the lookup table and then do a translation or not, depending. So there's another set of there's another lookup involved, which just makes the system bits running slower. So hence, it's disabled per default. So, okay, that's the theory. But how do we do this? Hang on. How do we do this in Qemu, or how do we simulate this and enable this in Qemu? Well, Qemu has Qemu has a special mindset. So whatever you do in Qemu, it has to work on all architectures, or at least the concept has to work on all architectures, even though the actual architecture in case might not have it implemented, but that's a different story. So it needs to work on, the concept must work on all architectures. So in our case, it means we need to take into account every IOMMU which is out there for every architecture, which is a tricky task. And there are some really strange IOMMUs, like the PowerPC. Is Alex here? No, he's over there. PowerPC has a really weird notion on how the IOMMU is supposed to work. So you do need to do some abstraction. And the concept they came up with is called VFIO. VFIO is just abstraction for virtual function I/O. So this is developed by Alex Williamson, or rather this has been redeveloped by Alex Williamson, because there's an earlier implementation of VFIO by Cisco, which is several years old by now, which originally Cisco did use for their virtualization thing. It never really took off, as far as I know, so it was just laying there. Then Alex resurrected the idea. So the concept is, the trick with that one is that we can utilize the user space I/O here. The Linux kernel has a user space I/O. I'm not sure if anyone's familiar with that. Probably not. Yeah, of course you would. Okay, so basically it means that you can run a driver in user space, and that you only have 2 hooks into the kernel, which is a, so basically you can do address mapping in user space via mmap, and you have a special file descriptor called eventfd, which allows the kernel to pass interrupts to user space, which is quite helpful because that's what you need for drivers, but can also be used in this case because you do need the interrupt somehow being routed to your guest. The hardware doesn't do it for you. You have to somehow notify the guest, hey, there's an interrupt. So, and the other thing is what he did was to implement something called device groups. Reason for this, shut up, I don't, right, okay. Device groups are required here because, as mentioned, this thing has to run on all architectures. And the thing is that not all IOMMUs on all architectures are able to address individual devices. On PowerPC, for example, it can only address device groups. So several physical devices are lumped together in a device group, and the IOMMU works on all of them devices simultaneously. So you can't split that up, that is a hardware limitation. And to map this, you basically have to implement something called device groups, which on Intel platforms just degenerates into 1 group per device, but hell, you still have to do it that way. So this whole thing is implemented in a new driver, VFIO PCI, which is present in 3.7 at least, if not 6, presumably 6. And well, this is just a PCI driver without any PCI-specific information, so it won't bind to anything. You have to do it manually if you want to do it. The usual trick of echo eins and bind doesn't work because it has an empty PCI table, so you actually have to fill in the PCI vendor and PCI model into that driver via this new ID trick. And if you do that, it will actually bind to the device, which then is a nice thing because you do get a dead simple command line for Qemu. This one is a Qemu. It's the command line for my Qemu guest I run in the lab, which has 2 devices, one IGBVF, the virtual function of the IGB driver, and a megasas, also both fully emulated. No emulation, nothing, all runs on hardware. That's really nice. It looks just like a real machine. Just there, boom, there you go. Ta-da! Just boots up the system. That's the BIOS of the megasas coming on. System boots, fine. That is nice. So, but however, as I mentioned, yeah, the whole things we did, as I described at the start, like Virtio and TCM Vhost and whatnot, are all concepts which look as if they should make the machine faster. It's not that anyone has ever measured it, simply because they always invented a new abstraction for doing the emulation. So it's really hard to measure because it's not the same system. You can't actually, well, sure you can measure it, but you measure something completely different. So you wouldn't even know if it's remotely comparable, even the results you're getting. So we could make things faster here, but again, we do have several layers involved, and to make a proper I/O performance measurement, we would have to measure each of those layers to figure out, right, where is the latency? Where does it make sense to improve things? Because if I would go ahead and say, oh, now I need to improve the Qemu block layer because I don't like it or because I think it's too slow, if that's only a fraction of a % of the entire I/O latency, I could as well leave it. Where's the point? I will never gain any advantage out of that. And to do so to figure that one out, we first have to do a performance measurement. So we could be using blktrace here, because that actually gives us a clear indication where how much time at each I/O request spends on each individual layer. However, this has some disadvantage or impediments here. The one is that Qemu isn't measured here. So because Qemu runs in userland and the userland isn't traced with that, and that it's a blktrace only gathers local information for the running kernel. So if you're running under Qemu, if you run this thing under Qemu, you have two kernels running. You have your guest kernel running and your host kernel running. Both will be getting you a blktrace information, but it's really hard to synchronize both because, well, which I/O again maps to that one in the other trace? That is tricky. So, however, what we could be doing is do a comparative measurement, as we are now able to simulate actual devices and actually map the devices directly to the guest. We could just have 3 or 4 setups, one fully emulated, one with virtualized SCSI with IOMMU, and one with VFIO, and measuring the overall latency for each step. So with that, we can figure out, at least roughly, where the I/O latency lies. Comparing the first two will give us basically the overhead of the emulation. Comparing the second and the third will give us the overhead of the IOMMU, because, as said at the start, the IOMMU should incur a higher latency, but how much? No one knows. There is no data. Or do you have some, Mel, for IOMMU latency? How big the decrease in I/O performance is?
Absolutely no idea. It varies considerably. And the first generation algorithms was very serious. It was before the IOMMU was the largest amount of overhead.
Yeah, but Calgary had their own IOMMU stuff. So the recent generation should have pretty decent speed, but again, no one knows. So, yeah. So, measure and comparing the third and the fourth will give you the difference between the emulation and VFIO. So with that, we could actually do some nice some comparison here and figure out where it would make sense to improve things. What we could do also is to extend blktrace to actually see whether we can't match the blktrace information from the guest to the host. Thing is, something like virtualized SCSI has a tag field which is just a 32-bit value, or where you can stick any information. So we could stick in an identifier for the request and have them display both in the host and the guest, so we would know, right, this node request X and this request X maps to this request on the host. So with that, we could actually mash up the blktrace information so that we have a full measurements of the full stack from guest userland down to the hardware. So, and well, the problem with that is obvious that another problem is the timestamps, that each blktrace has a timestamp on the I/O request, and the timestamp in the host and the guests are obviously different. So you would need to insert some synchronization point to know exactly which time in the host refers to which time in the guest. If anyone has a clever idea how to do this, I'm all ears, because I still don't know how to do this exactly. Sure, you could do something like NTP on both sides and hope, right, it'll get it roughly okay, but then NTP doesn't have the highest precision, so I don't think it's up to that task. So with NTP, you probably get a precision in down to seconds, roughly with a bit of luck, milliseconds. At least
by jitters.
Yeah. So, but it'll jitter inevitably. So that you can't really use. So you really want to get it down to a precise timing here. So, not sure. I have to think of it. Yeah.
You could use some form of round trip between the host and the guest, and then divide the time by 2.
Yes, you could, but this is only approximative. You won't be getting the offset with that. If you do a round trip time, you only know how long it took between Basically, you're just measuring the round trip time. Okay, it just took me, say, 4 seconds to get from the guest to the host. And at any time between those 4 seconds, the host has received the message. What you would be doing and would be needing is to figure out exactly the offset here. So when exactly did the host get the request? How long does it take for the host to process it? And when did it get back? So to get the actual offset, which is the tricky part.
Potential one there, the PTP time protocol. There has been work to implement that on KVM already.
Yeah, you could yeah, that's probably a good idea. Use the PTP one, because that's precisely the use case, isn't it?
Yes.
I haven't really looked into PTP, but yes, that's probably a good idea. Yeah, all right, good. Any more questions here? Because actually, that's the first talk done. Yeah.
Regarding IO. Regarding.
You have to talk really close. It's actually on.
With IOMMU, I'm more familiar with traditional MMU. Before the hardware extensions, there were shadow pages to translate guests to physical addresses. And with the extensions from Intel and AMD with nested pages, sure, you do have a performance benefit, saving the VM exits and having the host having to keep up with the page tables and the guest. But it also introduced the 2D page walk. So depending on the performance, the workload characteristics, you'll either have a performance gain or a loss. Does any of this translate into IOMMU?
It actually does, yeah. Because with IOMMU, you have the very same problems all over again.
Okay.
You have the very same concept. You have to have you have additional page tables. You have so you need to do an additional page walk, IOMMU page walk. You do have an IO TLB where all the lookup is being stored. The IO TLB is of different sizes depending on which CPU you're running on. AMD has some insane amount, so you basically never need to flush the IO TLB because you're never able to fill it. And on the Intel side, you have an insanely small IO TLB, so where basically basically nothing fits in it, so you have to do a TLB flush virtually on every access. So yes,
it's basically the same, yeah.
It's the same all over again. And this is exactly, no one has ever done any measurement here. So it's just so really broad thumb. Yeah, it looks as if, let's see, yes. And I want to do it anyway, so most go ahead and program it without any real backing, whether it's faster or not. Like the TCM Vhost stuff. Yeah, it looks as if it were faster, but whether it's really faster, who knows?
One would expect that we're just running a target workload, and then if the number is better, we just have, they don't care that some component of it is completely wrecked.
Yeah, sure. You will always be, there will always be a workload dependency here, and all performance measurement is only the specific workload you're introducing, which you're measuring here. This is in no case a general one. Okay. Sure, I mean, this is normal performance measurement. You always have this problem. And even for measuring the IOMMU, it's even getting worse. It might well be that your test case you're running is geared up for one specific IOMMU implementation and not for the other. So you might inadvertently just hitting the sweet spot of the IOMMU, but you wouldn't even know because, well, you don't, well, at least I don't have that much internal knowledge of how the IOMMU works here.
So nobody has benchmarked if it gives a real performance boost.
What?
So you said that nobody has really benchmarked the PCI pass-through stuff, the virtualization, if it really gives any performance boost.
Well, the idea here is that it does.
Okay, but it takes away, I mean, no longer...
It's simple. You're just taking away quite a few stuff, so it must be faster.
Yeah, and you're taking away one of the biggest features of virtualization. I mean, you can no longer migrate the machine.
Yeah, and here we go, the migration stuff again. Yay, you can't migrate. Hey, you're dumb, you can't migrate. I don't care.
Well, why do you
as easy as that.
why do you want to virtualize at all if you don't want to migrate, for example?
For once,
And
it's
not
by-
only migration. I'm sorry to interrupt you, but I mean one of the benefits of virtualization is that you get hardware abstraction, basically.
Yeah, and this is the age-old battle in virtualization. What do we want to achieve with virtualization? Do you want to have a random virtual guest which provides a hardware which you can talk to, which will run anywhere, which is basically the totally virtualized concept. So you're running on abstract hardware which doesn't exist on the real world but gives you the best performance? Or do you want to emulate a real machine? So, because then I can just run it everywhere, and it's just nicer. And it might well be that this hardware, that I do need to have access to this hardware, which doesn't exist anymore. Like IBM mainframe. IBM mainframe had their own, the horrible old X500 drivers. What is the name of that? The old SCON ones. They had this specific transfer mode. The OC network cards. You didn't know about it?
Not in the terms you're using, no.
Oh, right.
Are you talking disk I/O?
No, network I/O. The old network driver.
OSM.
Yeah, yeah, exactly. OSM. Yeah, that's it. So there used to be real hardware doing this, doing the OSM for the OSM card, but then eventually the hardware, the main manufacturer of that hardware went out of business. So there wasn't any, they couldn't get any of the hardware anymore. But there were still, their support contracts still were running for another 10 years. So they had to provide at least something to make this work again. So they actually had to emulate the whole thing inside the machine, just so that they have a driver which just looks like an OSM one, but in fact was just totally different hardware. Anyway, so yeah, but I mean, that is the whole idea of the Qemu stuff, to emulate things, isn't it? So I mean, this is Qemu, which emulates tons and tons and tons of things. Why would you want to emulate, say, an SH4 or whatever, AMD Voyager? Who cares? Because if you either you do a virtualization thing, then you should do the virtualization and do it good, or you want to do an emulation.
Device pass-through into an emulated machine.
Because then you can do a logical partitioning on the machine. You can run several independent instances on the machine.
The fact that there's plenty of use cases where device pass-through is preferred, and one case is where you just want to consolidate workloads onto a machine but have them fully isolated without the use of containers, in which case each individual machine should run as quickly as possible. However, there is no use case to migrate because it runs for the duration of the job and finishes. There are cases where people simply do not need to migrate a virtual machine, nor do they need the option to be available, but they do need the virtual machine to run quickly.
Like, I mean, PowerPC runs virtualized all the way. It has an ALPA. You can't migrate an ALPA. Everyone's happy with that. No one cares about migration here. That's, oh, I'm finished. No, we can talk about it later. But yeah, I mean, this is the, you always get into this battle. Do you want to do virtualization or do you want to do an emulation? They are close, but not identical. Right. Okay, so now